So again, what conclusion can we make if we know the value of 2 points in the graph and they happen to have these numbers? Again, this is a 5 here. Nobody? The root is between them. How come, Victoria? There's a reason. Look at the numbers. Claudia? It's between them and the x value. Sure, that makes sense. I'm sorry. The root itself will be between 3 and 5. Absolutely. Absolutely. But what indicates that the root actually exists there? Absolutely right. Look at the sign of the y value. Isn't this one positive? Where's a positive y? Isn't it above the axis? And then if the next one is a negative, that means it's below the axis. How do you get from above to below the axis? You cross the axis. You can't jump over, right? Again. So there must be a root there. What you've just learned, believe it or not, is a term in calculus. And later on, we call it the intermediate value theorem. Okay? But it's extremely important that you understand what this is. The wording doesn't matter. Intermediate value theorem right now. But because that is a positive negative. Claudia, because there was 3 and 5, this must be a number between that. Yes, that's all right. That must be a number in between. So who can give me an estimate of what the root might be? 4. Okay, take a guess. Doesn't matter there. Okay, are we clear? Again, that was, Claudia, I'm glad you said that because I wasn't even going to make that point right away. I didn't even think about that. I was more concerned about the positive and negative. But you're absolutely right. A good way to estimate, okay? All right, continuing. What we're going to do today is locate these values. Even if it's x to the 4th, even if it's x to the 5th, we can still find ways to do this. That's the cool part. Remember the quadratic formula, everybody? Okay? There is a cubic formula. There is a quartic formula. The quartic formula is about 1 entire page long. I'm serious. Look it up. Wikipedia or Google, quartic formula or cubic formula. Okay? If you check either of those, they will both be about a page, maybe a page and a half long. That's when you get into real proofs later on. You're going to see these kinds of problems. Okay? I'm sorry, you want to see it?
No,
I can pull it up right now instead.
It's going to blow our minds. We're not ready.
Can you go leave it in there? Sure. I can tell that it's really bothering you.
What?
It's reliable.
No, for math and science, it's actually very good. I would honestly say that. I really would. For math, Wikipedia is great. You know why? Here's why, seriously. And this is going to sound really weird. The reason Wikipedia is good for math and science is math and science people are usually technology geeks. Think about it. Think about engineers. I know myself, I love computers. Think about engineers and mathematicians. They're usually good with computer science or with hardware. So the people that make Wikipedia are all the users. Wikipedia is made by users. And most people that aren't computer geeks aren't going to be people that are going to be uploading to Wikipedia. Would you agree? If you didn't know much about a computer, are you going to be one of the editors for Wikipedia? But anybody can be an editor. I can go on Wikipedia, edit it, submit it, and if they approve it, they'll add my edit to it. I can make a page for a new topic that I might want to invent. As long as I have evidence for it that makes sense, they might approve it. You can put yourself on Wikipedia. I know somebody that did that. Their cell. If you have enough qualifications or expertise in something that you can prove that you should be on Wikipedia. I know somebody that was on there.
What was it?
One of my friends from high school. So let's go to this, guys. Let's take a look.
Yeah, you can only Wikipedia too.
If we have a quartic equation, so x to the 4th, we now don't have a, b, and c. We have a, b, c, d, and e. Notice there are 5 coefficients because it's x to the 4th. So let's see if the formula is hopefully on here.
Those are a lot of equations.
Just that symbol looks like a 1.
Sure.
All right. So these are all different techniques that you're going to use on quartic functions. They're not all about root finding.
Just pictures of it. Hey, do they use that method to make Ferraris?
All right. So here, take a look. if you follow this down from here down, all the way down to Ferrari's solution, that's the one solution to find the roots right there for quartic. For, let's try cubic. Cubic is obviously not as long.
Looking at Volkswagens, trying to do something back.
Here's the roots of a cubic function. The general formula for the roots is here. Okay, so I mean, like, it's not short stuff. That's for a cubic function. You don't want to have to go through all that work. There's a lot of work there. Now,
Love math. Yeah.
so, in order to bypass annoying, tedious legwork that is really not worth it, you can always use a calculator, absolutely, always. But I'm going to show you a technique today with the synthetic table. What the synthetic table will tell us is where the roots are located guesstimating. So, like, if you know a general idea, if they're integer values, it'll tell us the exact value of the roots. Okay? So we'll use a table today to show that on a synthetic table that we'll check on our calculators.
Oh, I saw.
You saw what? Functions? Yeah, see, we're going to get to those in like concept 50. Why, are they on the SAT?
No, I saw it, but that's not good.
Oh, yeah, square root functions and cube root functions look like a parabola, but imagine a parabola turned to the side. That's the square root. Imagine a cubic turned to the side. That's the cube root. We'll learn about this a little later. The quartic formula would be used to, like, find the roots of a quartic equation. You're never going to do that. You're not going to do that. Unless you become a, theoretical mathematician or something. Or you're not doing, like, applied science. You would never use that. All right. So, today what we're trying to do is find those roots. Now, what I want you to recall is this. Or can somebody just read the first note, the asterisk? Come on.
Because that when the value of the remainder is 0, there's a number that tells that the table is
We talked about this the other day. If the remainder is 0, the remainder is also the y value, isn't it? So if the remainder is 0, it means the y value is 0. When the y value is 0, that's what a root is. Just like that root up there. It would be 4 comma 0 if we were estimating. So when the remainder is 0, we have a root outside. Is everybody clear? So our goal today, our entire goal, is to get a 0 in that last spot. Juliet. We might have. There's a good chance one of your homeworks had a 0 at the end. Yes. It's very possible. I don't know off the top of my head, Juliet, but it's possible. All right. Let's take a look at number 1. First, if we're given a root or a factor, that's the type of problems we're going to look at now. So this problem says, if x plus 4 is a factor of x cubed minus 5x squared minus 22x plus 56, find the other factors. Based on the factors, what are the roots of this function? Now, please remember what factors are. Factors are like x plus 2. That's one of our factors. Or x minus 3. That could be a factor. One of our factors could also be like a quadratic. You can factor out a quadratic, believe it or not. So, to do this, we have to think about the correlation between a factor and a root. A factor and a root. So, if I were able to factor something like this, if I had x squared minus, let's say, 5x plus 6, can somebody please factor this equation?
Put your X's on the outside.
Okay, what are the numbers? X is on the outside, clearly.
minus 3. Yeah, it's plus
Minus 2. Some of you got it. Again, those are the factors. The two numbers that multiply to give you 6 and add up to negative 5. Now, what are the roots? If these are the factors. 3 and 2. Again, 3 and 2. So the roots are 3 and the root is 2. You have two roots here. Now, if you have the roots, again, if you have the roots, you also have the factors. You can go backwards also. Are we clear about that? Assuming that the root itself, the factor itself, is a linear function with a 1 in the front of x. with a 1 as a leading coefficient. If it was a root like 2x plus 4, I'm sorry, a factor like 2x plus 4, the problem issue, or the issue that would come up there is this. The root here is negative 2. Because you have to subtract 4 and then divide by 2. Again, the root is not negative 4. So see how this number doesn't switch anymore? Whereas here the number just switched. So when we do this technique, we're going to be talking about things like this, where you have a 1 or a unity value as the leading coefficient. Unity, 1. Unity value as the leading coefficient. Now, to do this problem, we want to think to ourselves, okay, if this is a factor right here, if this is a factor, then what is the root? Everybody, what's the root if this is a factor right here? Negative 4. If the factor is x plus 4, just like we said a minute ago, the root became the opposite of that value. So the root is clearly going to be negative 4. So if I put negative 4 through my table, what should I get as a remainder? 0. Again, the remainder is 0 when the value on the outside is a root. So to show that, here's what we will do. So let's begin our solution. We're going to say negative 4 synthetic table of, sorry, no, it's not like a real command. Now, are there any zeros there?
Nope.
How come, Derek?
It's already in like, it's already in, it's at the highest power.
Okay, so it's in standard form, and what else? Nothing's missing. So yes, it's in standard form, but there could be stuff missing even if it's standard form. So, with that said, let's do this. Bring down the 1, not the negative 4 like I did last time. We get negative 4 minus 5 is negative 9. Negative 4 by negative 9 is 36, minus 22 is 14. It's going to be negative 56, and 56 is 0. We got it. It did work. Now, you're going to say, well, what does that do for me? It doesn't do that much. It actually does. It does a lot. What this tells me is that there's your quadratic, right? Remember how we brought this down the other day with division? Remember how we made this x squared minus 9x plus 14, and then we have plus the remainder over here with division? The remainder over the divisor? Well, you know what? The remainder is 0. So this means this goes into it evenly. So if this goes into it evenly, it means that this thing up here is really factoring into this with an x plus 4. Again, where does the x plus 4 come from? This is the other root right here. This root indicates the x plus 4. This row indicates this quadratic. Is that cool? And we just factored it. Now, if we want to keep going, we just look at this and say, let's factor. Anybody got the numbers for me on the quadratic to factor? 2 and 7, both negative. Very good, Vic. 2 and 7. And we're done with the problem. Pretty cool stuff. Okay? Does that not amaze you though that a table that somebody somewhere along the way invented is able to do this for us? I think that's pretty, incredible to think about. I don't think I could think of this. The original table, guys, has been around for a long time. These methods have been used for hundreds of years. This idea of a table in this direction, Mr. Smith came up with. The other tables are inverted. It's the same concept, though. He just adapted it to this way. And you're going to see why later. Because what if this didn't work to give us a root? We know it's going to work because it's here, right? But what if we just tried a number, we didn't get a root? We could try another number and get another answer. Try another number, get another answer, and we can make a running table. And that's the goal for tomorrow's lesson, really. Okay? That's really the goal for tomorrow's lesson. We'll see how we do. Maybe we can start it today. Next page. Oh, I'm sorry. We should also mention the last part of the question. Based on the factors, what are the roots of the function? Well, one of the roots is negative 4. What are the roots from these two factors here? 2 and 7. Very good. So negative 4, 2, and 7. Those are your roots, again, from these three factors. It's very important that we note that, okay? All right, let's go on. Number 2. Can somebody read for me, please? Julian?
Here's the example.
Yes.
If x is equal to 1, if the root of fx equal to x cubed minus 4x squared minus 15x plus 18, find the other roots of the function.
Okay. So we're told that 1 is a root, aren't we? So shouldn't we just do the same thing as last time?
Yeah.
Next time we were told about a factor. Well, factor and root are pretty similar. So if we know the root, just put a 1 outside now. Again, just like last time. We knew the factor last time, we put the opposite of the value. Now we know the root. Do we have to flip the sign? No. Remember, out here is always the root. The root goes out here. If you were given a factor, you have to switch the sign to get the root. That's why we switch the sign. But here we leave the sign alone. So again, remember the other day I made a table and it looked like this. I put an R out here, and then I put A, B, C, D up top. I used the letter R because later on I was going to reference the root. That's where R came from. I didn't want to give it away just because we didn't actually cover that yet. It might have been a little misleading.
I thought it's standing for the main guy's name.
Oh no, I didn't even realize that. No, it's a lowercase. If it stood for a name, it would be like capital. Okay? Like laws that are named after people are usually capital. Like Faraday's laws and stuff.
Very elegant.
Mr. Bob, why is the one not negative?
Because it already is a root. This is a root. If you were given x minus 1 as the factor, then you would say switch the sign, and it's positive 1. But this is the root. You don't switch the sign. Again, last problem, we were given the factor x plus 4. And remember we used negative 4? We switched the sign because it was a factor. Because to get from a factor to a root, you have to switch the sign. But if you have the root already, like we do, don't switch the sign. There's no need.
You need an answer.
What do we got here, guys? 1, negative 4, negative 15, 18. Numbers, somebody give me their row.
1, whoa.
Is that what everybody got? I agree. That means that's one of your factors. What was your other factor? What was your root? It was 1, right?
So it'd be x minus 2.
Now, just because x equals 1 is a root, does not mean that x minus 1 is a root, is a factor, Again, because watch what I do right now. If I don't want x minus 1, what if I said this? What's the root for that? The root is 1, isn't it? Put a 1 in. 2 times 1 is 2. 2 minus 2 is 0. The root would be 1 if you solve that factor. So this root can have an unlimited amount of factors, as long as these numbers, a and b, are the same. Check that out. Think about it for a second. Try 3 and 3. You move the 3 over and divide by 3. It's still 1. Try 4 and 4. As long as the value of a equals the value of b, you can have an unlimited or an infinite amount of factors from the root x equals 1. Same goes for any other root. Okay? You can have any multiple of the root, of the base root, of the base factor x minus 1. It could become that. It could become... All of those factors have the same root, but clearly they're not the same factors. So if you have the root, you can't really go back up to the factor. Okay? If you don't know about the factor. But if you have the factor from the last problem, you can go down to the root. Again, remember, this root could have this factor, because this turns out to be x equals 1 if you solve it. If you solve this one, it's also x equals 1. Solve this one, it's also x equals 1. So any of those factors can really go here. So we're not going to write down the factor this time. Is that understood? Okay, so don't write the factor down this time, because you're not really factoring that. But now we do have to factor this to get the other two roots still. So please go ahead and factor this, but don't carry down a factor to the right, like we did last time. What do we get here? And most of you got that already, I hope. Again, negative 6 and 3 is negative 3. Negative 6 times 3 is negative 18. Julia.
So if you have a root that's like 1, you don't have to put it on the other side.
Correct. Because it was given as a root. Julia, the number has nothing to do with it. It's the fact that it was given as a root. Here, in the previous problem, it was given as a factor. So you knew that this was a factor. We got the root from the factor, but you can't do the reverse. If you're given the root in the beginning, like here, you cannot come up with a factor because there are a multitude of factors that it could become. We don't know for sure which one it would be. Okay? Jason. Yes.
So when you're doing the root, don't put it there, or is it just the kind of the 1?
when you're given the root, the word here is the root. It has nothing to do with the number 1. I apologize if that was misleading. And for any number, if you're given the root, you use it in the table, but you don't write it down here as one of your factors, really. It's not going to hurt you. It doesn't matter, because the problem doesn't even ask about factors. It asks about the roots. So I don't even care what is over here, really. I already got the root. Here's one of my roots. Now just find the other 2. Okay, so go ahead and find the other 2, please. Very good. Again, just switch the signs, please. -3 and 6. So there's 1, 2. If I slide up, there's the 3rd root. Why are there 3 roots, people? It's cubic. It's x to the 3rd. So you can have 3 roots at most. You could have 1 root. You could have 1 root if the other 2 are imaginary. Again, if the other 2 are imaginary, well, they're not really roots. We don't really call them roots. Okay, we call them solutions. Roots are really indicating that they cross the x-axis. Imaginary roots don't cross the x-axis. If you want to see an example of that as a little preview, look at the bottom. Oh, I can put it on here. I'm sorry. There's an image we're going to use later on just to show you that for the imaginary stuff. If I put it on mine. No. I'll draw it later. Okay? But generally speaking, we have 3 roots. So we already know 3 locations on the graph. We know 1, -3, and 6. So I've got a point here, I've got a point here, and I've got a point here. That's at 6, 0. That's at 1, 0. And that's at -3, 0. Now, can anybody guess what we might be leading into with this topic? A little louder, so we can hear you. The running synthetic tables, yes, but I mean, what is this leading us into? What might we do after we plot the roots next? We might graph. Remember end behavior, guys? Remember end behavior? If you know the end behavior, you know which way the end's going to go. That's where end behavior is going to come in. This is x to the 3rd. It's positive. So I know that to the right it goes up, to the left it goes down. So I already know the shape of this graph. This is just a little preview. Okay? I already know the shape. And if I can figure out a way to determine the midpoint, I can figure out that this is really just a loop. That's all it is. Okay? But again, we're not there yet. We're just a little preview of what we're going to get to. All right. Let's take a look at what we will start tomorrow. Okay, we got, actually, you know what? Let's start the homework. Let's stop there.